Good afternoon and welcome to this webinar, Data Mining with R, with Richard Skeggs from the Business and Local Government Data Research Centre. I'll pass you straight over to him to get started.
Okay, thank you very much. Okay, we've got a few housekeeping items to go over to start with. We are going to talk, this talk is going to go on for probably about 40 minutes, and then there's going to be a 20-minute question and answer session. So, now, this talk is going to look at data mining with R. There's a lot of software out there, a lot of R packages that allow users to basically perform a variety of data mining techniques. We'll be looking at an overview at PreProcessing, Anomaly Detection, Association Rule Learning, Clustering, Regression, and Summarising. And we'll be looking purely with an R-centric view. So to start with, what is data mining? Most of you have probably got a very good idea as to exactly what data mining is. But it is basically the process to discover interesting or new and unknown facts from a large data set. So, to start with, what about pre-processing? Because when we talk about data mining, the first thing we've got to do, in effect, is get the data into a format that we can deal with. And within R, this is in effect the data frame. We can get data from CSV, from databases, whether that be from building up a select query or basically dumping a table directly into a data frame. And we can even create data frames from zip files, especially if the zip file may be too large to open. So how can we, in effect, get or pre-process this data? Once we've loaded the data frame, there may be a couple of functions that we need to parse the data. We have advanced parsing with Perl-like regular expressions. We can do simple character substitutions, and we can even strip out specific characters. And in the first line there, it's basically stripping out the new line character \n from our data frame, which is X. Another thing we may have to do is coercion. When we're talking about numbers, if we're getting data out of a database or even from a file, are we sure that number characters are being treated as numbers? In the first case, what I've basically done is I have created, in effect, an array. And these are, okay, that's in effect 4 numbers, but they're not. By using the class function, I can see that they're being treated as characters within R. So if I want to make sure that I'm looking at numbers, I can coerce my character array into a numeric using the asNumeric function. dates are also another very, well, probably the most common form of coercion, is trying to get the date format right. If we're talking about getting dates out of Oracle, date or another sort of relational database, the date field may be coerced into one field, into one data structure. But if you're trying to blend that with another data field, that may be coming out in a completely different format. So what I've got here is I'm coercing, in effect, an array of dates, and these are stored as strings, and I'm coercing them into a date format using the asDate function. So again, how do I format dates into something that is more associated with the European time date timestamp? I can do this by using the format function right down the bottom. I'm taking the system date and I'm setting up my format structure into day, month, and year with a backslash as the separator. Now, within preprocessing, within dates, these are the variables that I can use within the format of the date structure to get either a 4-year, a 4-digit year, 2-digit year, whether I want a full month, an abbreviated month, and also use numbers, so using 2-digit numbers for the day of the month. When we'll see this a little later on as well when we start looking at some exercises, is that we will be looking at how to deal again with missing values. Now, when we're talking about large data sets, then data may not be complete, often isn't complete. So within some of the functions within R, especially when we're looking at k-means, k-means expects a full, in effect, a full data structure and does not like blanks. So how can we deal with blanks? We've got the option of using NA_fail and our data object to basically return an object only if there are no missing values. So that becomes a test. And with na.omit, we can actually remove data sets or lines of data out of the data set which are incomplete. But that may not be possible. The data that's missing, we may just want to use a special null character or a null identifier. And there are a couple of ways of doing that. Within a specific column, in this case, if we're looking at the iris data set, which comes within RStudio, I can basically look at species of a plant, and I can set the string null to where data sets are missing. So, having just gone over very briefly sort of the pre-processing, probably the next step we're looking at when we are data mining is anomaly detection. How do we detect anomalies? They don't have to be bad data. It could just be extraneous data. It could be valid, but we don't have to ignore it. At some point we have to try and understand where an anomaly has been created and why it's been created. And within R, there are 10 packages, roughly 10 packages within CRAN that handles outliers. Probably the two most common one, TS outliers, which is the one we'll be looking at. And this uses time series, uses data over a time series. There's also the Outliers package, but there's within GitHub, and there's the URL, there is a Twitter developed Anomaly Detection package that can be downloaded and installed. But we're not going to be looking at that. We're going to be looking at how to use TS outliers. So as I said, TS outliers in effect uses a time series. It uses the general procedure for detecting outliers, and we can use innovative outliers, additive, level shifts, temporal changes, seasonal level shifts. All these types of outliers are considered within the TS outliers package. Now, TS outliers is not part of the standard package, but it is available within CRAN, and as a result, it's pretty easy to download, install. And with that, there is a data set to be used, and we'll be using that data within this webinar. So this page you're looking at now, in effect, is the screenshot from an R console. So what I have done here is I've loaded the TS outliers library, which is done by library TS outliers. I have loaded the harmonized index of common prices dataset that comes with this is readily available within RStudio, which is what I use, and is also readily available with the is also supplied by the TS outliers package. So what I've done is I've loaded the HICP data, which is what it's called. Within the HIPC data, there's the array 011600, which is the data set that I'm interested in. And just by typing Y, I can get a view of that data. Now, with what we're doing here now is trying to identify within that data set the outliers, and we're using additive outliers, level shift, and temporary changes. So I'm using the TS outliers TSO package. My data set, or my data frame, is Y. The types of change I'm looking at are listed there, and I'm going to do 10 loops through the main data frame. Now, as you can see, the output from the outliers basically identifies 3. I've got 2 additive outliers and 1 temporary change. It basically gives me the timestamp as to when these outliers occurred. So I've got July 2001 and July 2008 has been fairly common, has been sort of fairly consistent with month, and then we've got the June 2006. So from that data change, we have got 3 outliers, 2 in July, 1 in June, over a 7-year period. Now, I can plot that. I can plot to see exactly what these outliers look like. When we're talking about big data, pictures often paint a far better picture than numbers themselves. And here we can see the red dots. These are being identified as the outliers within this graph. The blue line shows the actual data itself. Then we can see the outlier effect underneath. And we can tell that by the first dot and even the second dot, the effect was very short-lived as we got the straight up and down. But the third dot, the third outlier, seemed to have a more prolonged effect on the data itself. So we're now looking for association rule learning. How do we find an association between variables? And how can we use this? How can we use this association? Now, recommendation engines often will use a form of association rule, but they're not the only types. There are a number of packages within R that are available from CRAN that are very good with associated rule learning. The ones that I've used here today are A-rules and A-rules viz, 2 very common used rule associated learning packages. Now, we've also got within R as well, freely available, we've got the what is called the adult data set, which is basically a census of incomes from the US government. And what I'm going to do is I'm going to look at the Yapori algorithm and how that works as an associated rule learning function for this data set, so that we can try and identify sort of frequencies within the actual data itself. Again, this is another sort of screenshot from from RStudio, and I've loaded the adult data into R. I've basically done that by the function data that loads data within the R memory, and to that I'm applying some parameters so that I can try and identify the rules. Now so I've got my data set, which is adult. I'm basically applying a list of parameters. I don't need to apply these parameters. I could just as easily set it up so that I just run it against adult. And the data set that comes out, again, gives me a view of the data that I'm looking at. It gives me a confidence interval. It gives me sort of min values, max values. It gives me sort of a very simplistic view. And from that, I can basically see that I am, that this thing creates 4 subsets. There are 52 rules that can be found within the data set itself. And using the summary function, I'm probably going to clear a view of exactly what the associated rule learning is doing. So I can see mean, median, minimum values over a number of quartiles, and I've even got a fairly high confidence level with this data set, basically about, as you can see, very high confidence level, about 0.9. So, using the plot function, I can now plot the data to give me a much better view of what I'm looking for. And I can see, and I've got sort of various shadings going on here to sort of, for confidence, for support, for lift. And this is variables from within the data itself. So to understand this graph more, you need to be able to understand the data that you are looking at. But this is just sample data. It's your data, the data that you'll be looking at, the data that you'll be analyzing, that you will be able to have confidence to understand exactly its makeup, its structure, and try and be able to identify the patterns within it. So we now can come on to clustering. And within R, these are basically a list of clustering algorithms that are supported. It's a long list of them. Certainly don't have the time to go over all of these today. I'm going to be looking at k-means. This is probably the most common clustering algorithm that there is. And it's, again, within classic R, is very easy to implement. And that's what I'm trying to get over today. Just how easy it is to implement the packages within R to perform the tasks that you as analysts will need to perform on your data to understand what you're looking at. Now, this is in effect a snapshot of the it's in effect a snapshot of the Iris data set that comes with RStudio. So this is already available within the R package. And it's often used as a way of demonstrating new algorithms. It's a way of getting people to understand how R works. So again, I am loading this data. I'm doing that again by using the data function. I'm reassigning Iris to new Iris, and I'm basically doing some pre-processing. I'm setting blank species to null. And then what I can do is I can then say I'm going to apply the k-means function that actually comes with R. I'm going to apply this to the new iris, and the data, the documentation around this data basically says that there are 3 clusters. And when we talk about using k-means, we're talking about clustering. How many clusters are there? But what I'll do is, if you do not know how many clusters, I can show you a very simple way of calculating a cluster size using yet another package within R. The unfortunate thing is, using this data set, the cluster comes back as a cluster size of 2 rather than 3. But when we follow the documentation around this data set and we use 3 clusters, we can see the size of the sepal length, sepal width, the petal length, the petal width. So we're looking at the shape of a flower. We can then see how the data tells us which item is in which cluster. So this clustering vector basically says this first item up to the 48th item are basically all within cluster 2. From 49 to 97, the items are predominantly within the first cluster, a couple within 3 and the second, and in cluster 2. And from 97 to 144, again, most of the clustered data is within the third cluster, some within the first. So, and then we have some statistics based on that, and we've also got within that available components. And these are the components that are available that we could use for determining the size of the cluster, the sensors of the cluster, the differences between the cluster size and how close clusters are to each other. But these are the available components. Actually, what I will do, I'm going to bring up our studio now. And as I said, there's an FCP package within our studio. I've already got this installed. This will allow us to have a look at the size of, or to calculate the size of the cluster. As I said, when we're looking at k-means, ideally we need to know the number of clusters there are. So I'm going to load our FPC library in. And I'm going to use a function, can't type, PAMK, PAMK. And I'm going to apply that to a data set D. And D, wait. Typical. If I load I'm going to load the iOS data set into D. Wonderful, not a numeric or data frame. So what I'm going to do is I'm going to do some pre-processing. So I'm going to say new iOS. Is the same as data iOS. Now let's try and reload that again. Okay. iOS. Species. So a bit of pre-processing. Let's try that again. Lovely. When you want something to work, it never does. But so instead of trying to work that data set into a data frame, what I'm going to do is I'm going to set the code here, temp dot best, and see. So that will then, in effect, from the data set, will try and create the best clusters. The NC will then give me the number of clusters that are available, and I could even plot that using exactly the same function as plot. And this will give me a plot showing the iOS database, or the database D. Now, taking this approach, I can create a dynamic cluster set. So it will work out which is the best cluster size for the data set that I am looking at. Get back to my slides. Now, probably the next thing to be looking at is classification. Now, there are a number of classification models that are available within other toolkits, such as machine learning within Java. But within R, we've probably got, these are probably the most common ones, about 8, 1, 2, 3, 4, 5, 6. There are 8 classifications, 8 classifications that are supported. Each has its own benefits, each has its own drawbacks. Now, the one that I'm going to be, we've already had a quick look at naive Bayes, but we'll be looking at that again within this little section. So, what I've loaded here within R is the package E1071. This gives me a very nice view on, or gives me a nice interface into naive Bayes. And here I have got a, in effect, the screenshot from our R session that I had open earlier that uses naive Bayes and the Iris dataset to create a classification on the Iris data. We've got, at this point, down the left-hand side, we've got, well, at both sides, we've got 3 of the common types of Iris that are being used, or that are being recorded within the data set. And we've got basically sort of the numbers that are associated with them. So if you can remember that the Iris data set here, we've got the sepal length, sepal width, petal length, petal width, and also the species as well. So we are taking first part of naive Bayes, we are taking the first 4 columns to predict the 5th column, the type. So if we know the diameters for the first 4 columns or variables for the first 4 columns, what is the likelihood that we can predict what type of Iris it is? Now within the predict we have got a number of functions that are being applied. These are the most common functions. These are probably some of the more common functions that are being applied within our table in our predict function back here. So within one R function, we've got a lot of power within these prediction algorithms to generate data, or to generate confidence in the amount of information that we are getting back. So that's it. I think we're going to have to go on to any questions if you do have any.
Brilliant. Thank you very much, Richard. We have got a few questions. There's someone asking how to download the data. I'm assuming the dummy data sets can be downloaded from somewhere. We can always put them up on our website so that you can get access to them.
Actually, the dummy data sets are freely available within either the packages that I have used, or if you're using RStudio, are available within RStudio itself.
Okay, it looks like they're specifically referring to the adult data.
Okay, that is, I will.
We can make that available.
I'll make that available.
We can make that available. We'll pop it up on the website for you. And also, people asking, are there any really good, concise guides to the pros and cons of the various algorithms and methods that you talk about?
There are a number of the resources within CRAN provide a very good overview as to the algorithms that are being used within this webinar. As for the pros and cons, no, I haven't come across one. It's basically been sort of, I've picked it up through experience. So I will have a look around to see if I can find one, but I have yet to find one. So sorry about that.
Okay, thank you. And are there any benefits over why you'd use R over other software for functions such as this?
No, it's just another tool set. If you've got a lot of R knowledge within house, then yes, stick with R. But is it better than using something like Java? I don't know. I can't answer that one. I would use both Java and R. Sometimes I would prefer R to Java. Sometimes R to Java. So no, there is no real benefit unless you've of this over Java or Java over this. All depends on the experience that you do have and the knowledge set within house.
Okay, thanks. Just while people are thinking about any other questions they might want to put in, is there anything that you might want to touch on for a few moments?
No, I don't think there is at the moment. I will have a look at trying to dig out some of the data sets for you, and making sure that they are available on the website. And I'll look at the trying to look at the pros and cons of the various algorithms that are being used.
Okay, so just give people just a few more seconds in case there's any more questions to come in. But like Richard says, we'll pop the we'll pop those data sets up on our website so that they can all be accessed freely, and there will be a recording of this which will be up on the website again in a few days' time, so you can always refer back to it and have another look at anything that you might want to revisit. So if there's no more questions, then we'll say thank you very much for joining us today and for all your questions, and thank you very much to Richard for his presentation. Thank you.